So today we are going to deal with some questions with drag force. Drag force means viscous force, or you can say air resistance force. In magnetism, there are few very good, two, three beautiful questions based on drag force. So what I'm going to do is I'm going to start with a very basic question of kinematics, where we have some air resistance, and then we will build up some concept with this, and then we will go to the magnetism question and solve them. So here, this is the first question. This is not at all based on magnetism. It's a question on kinematics. A ball is projected vertically upward with this velocity. So here is the ball. It is projected vertically upward with this velocity. Initial velocity is 20 meter per second in the upward direction, as you can see. It turns back to the ground. That is the point of projection. Here there should be bracket closed. Okay. That is the point of projection with a velocity of 16 meter per second. So it is projected upward with 20, and then it comes down with 16. So obviously there is some air resistance, because otherwise it would have come back to this level with the same speed of 20 meter per second with which it was projected upward. But that's not happening. Okay, it's coming back to that position with a smaller velocity. So there has been some energy loss due to the air drag, due to the air resistance. If the air resistance is proportional to the speed of the ball, okay, air resistance is proportional to the speed of the ball. So basically it says that this air resistance, which I'm going to represent with a force friction, small f, it's not friction, you can say it's air friction. It is directly proportional to the velocity of the ball along with a negative sign, because obviously it will be in the opposite direction. So you can say that this frictional force or air resistance force is negative of some constant, which I'm calling it small b, you can call it k, doesn't matter, into v vector. Okay, so this is the air resistance force, and you have to find total time taken for the travel. Now this question, you may feel that it requires some integration, because there is going to be some force. For example, I have already drawn this diagram. For example, look at this snapshot. Okay, let's say this ball, it is going up and up and up and up and up, and at a certain time over here you have taken a photo snapshot. So right now velocity will be in the upward direction. This is the instantaneous velocity. And what are the forces? Well, there is going to be, of course, mg is going to be one of the force, and in addition to this mg, there is going to be air resistance force, which will be opposite to the instantaneous velocity. So when it is going up, the air resistance force is going to be downward, which is opposite to the velocity. Now while it is coming down, so it has already reached its upper point. Obviously at its highest point, its velocity is going to be 0 instantaneously. Now when it is coming down, at this moment, you see its velocity will be downward. Obviously mg will always act in the downward direction, because mg has got nothing to do with the velocity. It's a constant force with which earth pulls the body towards it. So mg will be acting downward, but this time, since the velocity is in the downward direction, so magnetic force, sorry, not magnetic force, air resistance force is going to act in the upward direction. So this is going to be the air resistance force, or you can say frictional force, or you can say viscous force. So this is a variable force problem, and whenever there is a variable force, obviously we feel that we have to integrate. But there is a very, very nice trick. So what I'm going to do is I'm to use F net equal to ma as usual. At any general time, net force acting on a body is equal to mass of the body multiplied by acceleration of the body. Now here there are two forces acting. The thing is that I'm going to write everything in vector form. So mg as a vector, okay, as a vector. Of course, you can write it as minus j cap. That's fine, but deliberately I'm going to write it like this. So mg vector plus this air resistance vector. Now since I'm writing it with vector sign, so plus automatically means negative while going up, is equal to mass into acceleration. Okay, so so I'm going to move it on this side. So acceleration vector is equal to g vector, because I'm going to divide it by m, so gets cancelled here, and plus, or rather minus, b by m v vector, because this force is going to be minus b v vector. See, and I'm dividing it with mass. I'm dividing it by mass. Now I have to find total time taken. Okay, so this acceleration I'm going to write as dv by dt, dv vector by dt. Everything I'm writing in vector form. That's the beauty, and you will see why am I doing it. Then I'm going to move dt on that side, so I'll get dv vector is equal to g dt g vector dt minus b by m v vector dt, and then I'm going to put integration sign. Okay, now obviously once more let me write it. So integration of dv vector is equal to g vector is a constant force, so it comes outside integration of dt, and minus b by m is a constant, it comes outside this integration, so integration of v vector dt. Okay, now let's analyze each one of them. What does it mean? It means change in velocity. It means change in velocity, which is v final vector minus v initial vector. Okay, and what does this means? This means total time taken, because I'm going to integrate it over the entire period. Okay, if you want, you can obviously put the limit, but it's fine. I mean, this is a simple thing. So this is going to be what? This is going to be total time taken, which you can write as capital T. And what is this going to be? This is going to be displacement vector, S vector. Okay, now if you see in this integration, dv, what is the final velocity? And of course everything is in vector form, that's the main thing. So you see, this velocity minus this velocity is 16 minus j cap. Okay, you can write it in the vector 16 meter per second, I'm not writing the unit, minus what about this initial velocity? It was 20 plus j cap, because it was in the upward direction. And then g vector you can write as g minus j cap, because gravity acts in the downward direction. And dt is the total time taken, and minus b by m. And what is this displacement? And what is the displacement? Well, it's a null vector. It's a null vector because this is the starting position, that itself is the ending position. So we get the answer. We have to find the total time taken. This is the total time taken, capital T, and we get the answer in a single step. This is actually a single step. I am explaining it, so I'm taking so much of time. Otherwise, it's a single step. So obviously, this j cap and j cap and j cap you can cancel, because this is null vector. This is 0, and you get total time taken as, this is minus 16. Okay, this is minus 16 minus 20, which is minus 36 j cap. I mean, j cap got cancelled, sorry, and then minus g, which is minus 10. So you get 3.6 seconds, and that's the answer. So you don't have to deal with big integrations. Okay, so that is it. Now we will deal with the magnetism question. So this is the question. Let's read it. In a region of space, a uniform magnetic field of induction this exists. So magnetic field is, you can say, into the plane if you take k cap as outward direction. A particle moving with velocity v vector in this region experiences a drag force given by this. It's the same question, just that instead of b, they have used small k as the proportionality constant, where k is a positive constant. A particle of mass m and charge q is projected with this velocity in this region. Find its displacement when it practically stops. So let me draw our x and y axis, and let me start solving the problem. So here, let's say this is the x-axis, this is the y-axis. Just a sec. Come on. Yes, it's better. And because I have chosen this to be x-axis, this to be y-axis, so z-axis has to be out of the plane, because you know x cross y should give you z, because I cross j is k. Now magnetic field is given to be minus b k cap. That means magnetic field is into the plane. So this is the magnetic field, which is minus b, or rather I should say b is the magnitude and minus k cap is the direction. So magnetic field is everywhere like this, but I'm not drawing these diagrams because it's unnecessarily going to complicate the diagram. So I'm just going to show it over there. Now a particle is projected with this velocity in this region. Okay, so by the way, it's not given that it is to be projected from the origin, so you can project from anywhere, but let's keep it simple and project this particle from the origin with this velocity in this direction. So here is this particle whose charge is q and mass is m, and it is projected in this direction with initial velocity u I cap. So I'm just going to write u. Now, if the drag force was not there, for a second, let's ignore this drag force. Then you know this is a very well-known situation. The motion is going to be circular in that case, because obviously there is a magnetic field into the plane and the particle is moving in this direction. So there is going to be a magnetic force according to the formula q v cross b. That's magnetic force. And if you do v cross b, it's going to come out in this direction, and that is going to make it rotate in a circle. So if magnetic field, if drag force was not there, if viscous force was not there, then the motion is going to be a well-known circle. And we know everything about this circle. We know exactly where the center is located. We know the radius of this circle is mv by qb. We know time period of revolution, it is 2 pi m upon qb. We know angular velocity, which is qb by m. These are very well-known facts. But we have a drag force. So what will happen? This drag force, and by the way, one more thing before I come to the drag force, one more thing. You know that this magnetic force, okay, the magnetic force, for example, here magnetic force will act in this direction. Magnetic force will be perpendicular to the velocity. So magnetic force cannot change the magnitude. And anyway, work done by magnetic field is always zero. That's a you can say universal truth. It never gets violated. Work done by magnetic field is always zero. So if there is no work done, then kinetic energy, which is half mv square, has to remain constant. And if kinetic energy remains constant, you can say speed remain constant. So these are all well-known facts. So if there was only magnetic field, then this particle will move in a circle move in a circle with what kind of speed? With uniform speed. Speed is not going to change. So here if the speed was, let's say, 10 meter per second, here also it will be 10 meter per second, here also it will be 10 meter per second. Speed is neither going to increase nor going to decrease. But there is a drag force, and this drag force is always going to act opposite to the velocity. So it's going to reduce the velocity. Now if velocity is reduced, then radius must get reduced, because radius is mv by qb. So the radius of that circle will keep on getting reduced, and by now I think you must have got some idea that it's going to move in a spiral path, and eventually it's going to come and stop here. Okay, so this is going to be the path. So path is going to be spiral path. Let me show it. Let me try to draw a little better diagram if I can. So first the motion will be this way. So it's going to go this way, this way, this way, and eventually, let's say here, it comes to stop. By the way, in these types of cases, if they ask you the time before it stops, I think the time will come out to be infinite. Okay, but they are not asking time, they are asking displacement. So eventually it will practically come to stop. Then this is going to be the displacement vector. Which vector? This vector is going to be the displacement vector. We have to find this displacement in the vector form. In the vector form means you have to find its magnitude as well as direction. All right, first let me tell you how to find magnitude. So forget about the component, forget about, basically you have to find the x coordinate and y coordinate of this particle. Okay, this point where it stops. Just a sec. So it stops here, let's say, and let's say its x coordinate is x and y coordinate is y. So you have to find that coordinate eventually. Once you find the coordinate, then you can say displacement is going to be xi cap plus yj cap. Okay, but first, if they had asked you, only tell me how far it stops. Don't tell me in the vector form. Only tell me the distance. That means the shortest, the magnitude of displacement. Okay, if they only ask you, then what to do? So let me draw a diagram for a general time t. At a general time t, let's say the particle is here. Now at this time t, its speed must have decreased, by the way. Initially its speed was u. Its speed is not going to remain constant. So this vector size is going to decrease because of the drag force. Now in addition to this, okay, this is velocity. Now one force will be acting in this direction, which will be drag force. Let me make it a little thicker if I can. Yes. So this will be the drag force, and there is going to be a magnetic force. Magnetic force will still be according to the same formula, qv cross b. So magnetic force will be in this direction. Come on. Yes, this is going to be the magnetic force. Now just as I showed you earlier, I'm going to write the equation in vector form and see what we can get. See, I shown you earlier over here in this kinematics problem, that if you write this equation in vector form and don't break this vector form, then maybe there is a chance that you may get a very nice expression. So let's try our luck. So at a general time t, if I'm going to use F equal to ma, F net equal to ma vector. F net is what? There are two forces. One is this magnetic force plus one is this viscous force, is equal to ma. So ma vector, I'm going to reverse it. I'm going to write F on this side. So ma vector is going to be, now magnetic force will be qv cross b, and this drag force is going to be the proportionality constant v into b vector. By the way, here it's written k, but somehow I'm going to use b. Okay, now just like last time, this acceleration I'm going to write dv by dt, and this m I'm going to bring on that side. So q by m, v vector cross b vector, and minus bv vector, b by m, v vector. Okay, then I'm going to move dt on that side. So dv vector, oh, I forgot the vector symbol. It's very important to write this in vector symbol. Q by m, v vector cross b vector, dt, minus b by m, v vector dt, and I'm going to use the beautiful integration symbol. Now q by m is a constant, it will come outside. Okay. So let's put the limit here. Now initially, by the way, what will this give you? Forget the limits. Limits we'll put later. What will this tell you? This will give you what? This will give you the net displacement, and this will give you what? Okay, this one, I'll do one thing. I'm going to see dt is a scalar. This is a vector. I'm going to write dt over here, and I'm going to bring b outside. But I'm not going to break this cross product. Let this cross product remain. I'll just do a small manipulation. q by m. Here I'm going to write v vector dt. Okay, and this b vector is, by the way, uniform. Uniform means same everywhere. So this b vector I can take outside this integral. So I can write this as this cross b vector. This is where I have done this small manipulation. I brought this dt inside and b outside, and because b is uniform, so I can take this b outside the integration. Okay, and then minus b by m, and this integration symbol, and then this v vector dt. So what will this give you? This is displacement. And what will this give you? This is also displacement, because this is also this. And what will this give you? This is going to give you delta v vector, change in velocity vector. Okay, so I can write this equation as change in velocity vector is equal to q by m s vector cross b vector and minus b by m s vector. Okay, this is a perfect equation we got. Now, what is change in velocity? If we look at this as the starting position and this as the final position, in the final position v will be 0. Final velocity will be 0 because it has practically come to stop. So v will be 0. And initially velocity was ui cap. So I can write this as 0 vector, null vector minus u vector, which basically means u minus u vector, is equal to q by m. Okay, s vector I can write. Okay, let's see. So displacement I can write. Let me write here. Displacement I can write as, in vector form, displacement I can write as xi cap cross plus yj cap. Okay, and now I'm going to do some mathematics. So, by the way, before I proceed, just let me give you a hint. This vector, this is a vector, and this vector, because it is cross product, so this vector is going to be perpendicular. This vector is going to be perpendicular to s vector, and this vector is going to be parallel with s vector. So these two are orthogonal vectors, means they are perpendicular to each other. So if you simply want to find the mod of this, you can write mod of delta v, okay, is equal to 1 by m, if you take outside, under root of sb sine, this is, I'm not going to do it, but I'm just going to tell you, plus, this q is there, don't forget, q square, this, and b square, s square. I'm going to explain it in a moment, and then I'll leave it. But I'm going to explain it just a second, because it's very interesting. See, there, this vector and this vector are perpendicular to each other because it is a cross product of s and b, and this is s. When you take cross product, the resultant, the result, I shouldn't say resultant means summation, the result is always perpendicular to both the vectors. So this vector overall is perpendicular to s as well as b. We are interested in s, perpendicular to s, and this is parallel with s. So these two vectors are orthogonal. When they are orthogonal, if two vectors are perpendicular, which means orthogonal, then the resultant is going to be under root of this square plus this square. That's what I'm going to use it. So under root of this square and under root of this square is going to give you sorry, what did I tell you? Just a sec. Under root of this square plus this square is going to give you this, okay, in terms of magnitude. So in terms of magnitude, magnitude of change in speed, magnitude of change in velocity, not speed, is equal to 1 by m is a common, so I'm taking it common outside. Under root of this square, if you do s cross b, it will be sine 90 degree, because s vector is in the plane of the board and b vector, don't forget, b vector is into the plane of the board or plane of the screen. Okay, and plus this. So that way you can find magnitude of displacement. Okay, if needed, you can use that, but we are not going to use it because we have to write it in vector form. Okay, question was, if you read, find the displacement, means they are not asking just the magnitude of displacement, is asking the overall displacement as a vector. So better to solve it properly and get the actual answer. So so here you get delta v means final minus initial, q by m S vector, I'm going to write x I cap plus yj cap and crossed with minus bk cap and minus b by m. S vector again is x I cap plus yj cap. Now you can do it yourself actually. Acha, this initial I vector, I think even this m I can move on this side. By the way, this m, oh, okay. Okay. Just a sec. Just a sec. This q is going to go inside because I'm taking m common. Okay. And this m, because I have taken common, I think this is better because this m is common, so better to take it common. Okay. This initial vector, this I, and this m also I'm going to move it on this side. It is mu I cap. See, initially this was projected in the I cap direction. Is equal to, now let's do the boring thing, which is the cross product. So I cross k, I cross k, I j k, I j k, I cross k is minus j. So q b x j, there was already one minus sign, so that's why this minus is gone. And then j cross k is I, so minus q y b I cap, and then minus x b x I cap, and minus b y j cap. Is it fine? Am I doing any mistake? Let me just cross check. Q x b I cross k is minus j, q y b j cross k is I, so that's why this minus is there, and this. Okay, so q, why this q is there? Okay, so now let's add this I and I together. Let's keep this I together. So we are going to get minus qyb plus bx I cap, and let's write this j and j together. So plus qbx minus by j cap, and this is equal to minus mu I cap. Now obviously if the two vectors are equal, their I component should be equal to I cap component and j should be equal to j, but there is no j over here, so j should be 0. So from here we can write qyb plus this small bx is equal to mu, equation number 1, and qxb minus by should be 0 because over here there is no j cap is not there. So equation number 2, and now you can solve and you can get the values of x and y individually. So I solved it, and this is the answer you'll get by solving it. You'll get x as this and y as this, and this is the answer given in the book. So we got the correct answer. Now obviously over here it's written k instead of b because the proportionality constant in the actual question was k. So once you get it, you get displacement as x I cap plus y j cap, and that's the answer. Now we will solve the next question, which is also exactly the same question, but in the next question they have asked angle rotated. Okay, angle rotated. All right, this is the next question. Let's read it. A particle of, this is the same question, just that they are asking slightly different thing. So of charge of mass m and charge q is projected with a velocity v naught in a viscous medium where a uniform and constant magnetic field b vector exists everywhere in a direction perpendicular to the direction of projection of the particle. So if the particle is projected this way, then magnetic field may be either out of the plane or into the plane. It is perpendicular to the direction of the projection of the motion. By the way, it can be along y-axis also, but we will not take, if you have solved any magnetism problem, you know that most of the time we prefer to take magnetic field either into the plane or out of the plane because that makes our diagram easier. All right, so the drag force is again given by the same result, and okay, now the thing they are asking is, let me highlight it. Find distance traveled by the particle. Find distance traveled by the particle. Distance, okay, not displacement. Distance traveled by the particle during a time interval from the instant of projection until the velocity vector turns by 2 pi radian. 2 pi radian. Okay, enough of this coloring. Let me get on with the problem. So I'll draw the same diagram. I'll try to be fast if possible. So this is x-axis, this is y-axis. Magnetic field, just like last time, into the plane I'll take. Magnetic field this time, by the way, is not given, but we will take. And initial velocity this way. Initial velocity this way. This is the particle, q comma m. It's going to move in a spiral path. See, right now I'll stop. Why? I'll not draw further. Why? Because the question is, when the particle has rotated by 2 pi radian, 2 pi means it has come back to C. Initial, actually, when the velocity vector has rotated. So this was the initial velocity vector. This was the direction of the initial velocity vector. Here the direction of the velocity will be this way. Here the direction of velocity will be this way. Here the direction of velocity will be this way. Here the direction of velocity will be this way. So if you look at the velocity vector, it has actually turned by a full circle, the velocity vector. So that is why he's saying that find this distance traveled, okay, not the displacement, distance traveled, when velocity vector has rotated by 90 degree. So this was the initial velocity. Was it given? Was it given? Initial velocity, was it given? No, it's not given. I'm going to take it u, no problem, u vector. And this is the final velocity, v vector. Final arrow will be a little smaller. I'm going to call it vf vector. Okay, because I'm going to draw a general position. So at a general position, let's say the particle is here and it's moving with velocity v vector. This is the general velocity, general time. Now over here, the forces will act, and yeah, one force will act in this direction, which will be the viscous force, which will be minus bv vector, and one force will act in this direction, which is the magnetic force. This time, because you have to find angle rotated, all right. So we have to think in terms of angular velocity. We have to think in terms of angular velocity. Okay. Now, at a general time t, that means at this time, this is general time t. At a general time t, this force, what is this force doing? What is this magnetic force doing? Magnetic force is responsible for rotating this vector, this velocity vector. This velocity vector is rotating only because of this magnetic force, and velocity vector is decreasing in magnitude because of this force. See, two forces are acting and they have a different job to do. The job of this force, which is drag force, is to reduce the length of this vector, or you can say the magnitude of this vector. And the job of this force is to turn this vector, is to rotate this vector. You can call it centripetal force also, obviously, because it is acting at the center. So at a general time t, I can use FB is equal to m v square by r or omega square r. Both are same thing. But what is r? What is r? R is radius of the instant, radius of curvature at that instant. Okay, radius of curvature of the helical path, of the spiral path at that instant. Which instant? At time t equal to t. Okay, maybe I think it's better to write in terms of omega square r. It's the same thing, but so you will get qvb, which is the magnetic force, is equal to m, okay, v square by r only, because at least one of the v will get cancelled if I write v square by r. Okay, so here I am going to get v by r, where again, what is r? R is the instantaneous, that means at that time, radius of curvature. So v by r will be qb by m. And what is the meaning of v by r? Of course, you know it is omega, because world famous v equal to omega r. Who doesn't know v equal to omega r? Now, many people would not know in the vector form v vector is equal to omega vector cross r vector, but at least everybody knows this. So v by r is omega is equal to qb by m. Now, this qb by m, how many times it has come out to be omega? In most of this magnetism problem, even if you don't know anything, you can actually by blindly you can say omega will be q by m, and there is a chance you will be correct. Now, it's not that every time you will be correct. There may be 2 qb by m or qb by 2m, but there is a chance you'll be correct. Okay. Now, what is the purpose of this omega? What is this omega doing? What is this omega doing? This omega is rate of rotation of velocity vector. So this omega is rate of rotation of velocity vector, v vector. So I can write this omega as d theta by dt is equal to qb by m, and call it, leave it for time being. Okay, we have done enough, leave it for time being. Now let's focus on the tangential direction. As till now, whatever we have been doing in this orthogonal direction, now perpendicular direction. Now let's focus on the tangential direction. Along tangential direction, you see this is the force. So along tangential direction, now along tangent, I'll borrow this diagram, I'll copy this diagram, otherwise I'll have to scroll it many times, which I don't like. Okay, just for the sake of not scrolling up. So now tangential direction. Okay, along tangential direction, let us again use F net equal to ma. Let us again use F net equal to ma. Now this time along tangential direction, this is the only force. Okay, so I'm going to write minus bv is equal to m, and this acceleration I'm going to write v dv by ds. Okay, so one of the v will get cancelled, sorry, not that, this, and you will get m dv is equal to minus b ds, and then we can integrate it. Okay, so initially when displacement was zero, or rather distance, actually in this case it turned out to be distance, because when you write it in the scalar form dv by ds, here this s comes out to be distance. Okay, initially when the distance was 0, speed was u. Finally when the distance becomes s, okay, which s? This s from here to here. Okay, the speed comes out to be vf. Do we need it? No, maybe I don't need it. You know why? Because the question is to find distance traveled in terms of angle rotated. Okay, here I have got d theta by dt. Here, all right, now I understood. I don't need to write dv by ds. I can write dv by dt itself. Yes, that will be better. No? See, minus v bv is equal to m dv by dt. Or v dv by ds. V dv by, I think v dv. Let me continue with that. Let me, at least I was getting something. Let me continue with that. Okay. So I'm going to write acceleration as v dv by ds. We'll get, don't worry, we'll get. And then this b will get cancelled, v will get cancelled, and then you get dv is equal to minus, or rather m dv is equal to minus b ds, and we can put integration sign. When displacement was 0, velocity was u. When displacement was general s, velocity is general v. I'm going to write general v. I'm not going to use it till that moment. I'm going to use from 0 to t up to this moment. We'll see what happens later. Okay, so you get m v minus u, which is upper limit minus lower limit, is equal to minus bs. So you get v as, okay, u minus b by m into s. See, move this I m, so you get v minus u, and then move this u. Yep. Okay, so you got velocity in terms of displacement. Here, if you notice, this is the velocity at a general time t, and this is displacement, rather distance at a general time t. These are constant. This u was the initial velocity. Obviously it's not a variable thing, it's a constant thing. Now I'm going to write v as ds by dt. Okay, I think we should be almost done. I'm going to write v as ds by dt. So ds by dt is equal to u minus b by m into s. Okay, this is, call it equation number 2. I'm more excited because I think we are in the right direction. You see, where is it? Just a sec. This was equation number 1. This is equation number 2. If I divide it, then dt should get cancelled, and you will get s in terms of theta. Sorry. If I divide it, I will get s in terms of theta, and then, because eventually you have to find, let's go back and read the question. Eventually what you have to find? You have to find distance traveled, in other words s, during a time interval when, so time we don't have to find, okay, time interval is written, we have to find when the angle rotated is theta. So if you can find distance traveled as a function of theta, okay, if you can find distance traveled as a function of theta, then in theta we'll put 2 pi and we'll get the answer. So aren't we on the correct path? You see, we have got d theta by dt, we have got ds by dt. If we divide it, you'll get ds by d theta because dt will get cancelled, and then we can integrate, our job will be done. So divide, okay, divide what, you can divide 2 by 1 or 1 by 2, doesn't matter. So 2 by 1, so you get ds by d theta on the left side. See, let me copy this because some of you may not be able to see this. Just for ease of it, let me copy this. This was equation number 1. Okay, if you divide it, what do you get? You get ds by d theta is equal to what? Is equal to u minus b by m s divided by qb by m, which I'm going to write omega. Later I'll replace it. Okay, and also this b by m, again I'm going to write u minus ks by omega, where k is b by m and omega is qb by m. Maybe there was no need, but it's okay, it doesn't matter. Now we will separate the variable. So ds by u minus ks is equal to 1 by omega into d theta. So you move d theta on this side and this on this side, variable separated. Then we will put our beautiful integration sign. Okay, in physics, when you are able to put this integration sign, that means you have done the physics part. So you should be glad and happy that you are on the verge of solving the problem. Okay, initially when the displacement, or rather distance, was 0, angle rotated was 0. Finally, or at a general time when displacement, or rather distance, is s, angle rotated is theta, because our aim was to find distance traveled as a function of theta. So I'm writing as a function of theta. You can directly put 2 pi, but better to do it this way. Let's do this integration. So what do we get? You get ln u minus ks divided by minus k is equal to 1 by omega theta. Of course, you have to put limit 0 to theta, and here you have to put limit 0 to s. So you get ln u minus ks divided by u minus 0, upper limit minus lower limit. Okay, in place of s you put s, and in place of s you put 0, and this minus k you move to this side, so you will get minus k by omega theta. And now let's get rid of this ln. So you get 1 minus ks by u is equal to, okay, let's put this k value. What was k? K was b by m. So k was b by m, and what was omega? Omega was qb by m. All right, so you get e, because I am removing ln over here, there was ln ln, so this part will come to the power of e. So e to the power minus b theta by qb. So you will get k, again this k was what? This k was b by m. So b by mu s is equal to 1 minus e to the power minus b theta by qb. So finally you get s as mu by b, and then 1 minus e to the power minus b theta by qb. Now finally put theta as 2 pi and you get the answer. Distance traveled is mu by b, 1 minus e to the power minus b in place of theta 2 pi divided by qb. Okay, this should be the answer. Let us match the answer with the given answer. So this was the given answer. This was the given answer. It's fine. Initial velocity according to the question was v naught. I have taken u, so that's why. Otherwise, everything is fine. And by the way, some of you may be wondering, sir, what is this symbol? EXP. This means nothing but e to the power this. Okay, EXP is this another way of writing e to the power. Okay, some people call it EXP for exponential function. Fine. That's it. We have solved 2 beautiful questions of magnetism. Now there are many more questions of magnetism which I've given you in your assignment. You should do that.